Now, we have membrane potential down. What do we know is most important? Potassium, 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 potassium. Potassium is very important for resting membrane potential. Let's manipulate it a little bit, because you won't always have the same potassium concentrations, right? There are times when you have high potassium, there's times when you have low potassium. How does that change membrane potential? So if we have our cell here at -70, it's normally leaking out some potassium. That's very normal. Sodium potassium pump rotates some of it back in. If you were in a hypokalemic state, meaning that there is now low potassium in the extracellular space, so that's the interstitial fluid and the plasma, have low potassium. How does this change membrane potential? More potassium will want to leave the cell because the concentration gradient is higher. That hyperpolarizes the cell and makes it more negative. You can see the more negative here with an oscilloscope tracing. So what you're doing is moving more potassium out of the cell. It's getting closer to this -90 value. If you actually measure it, you can get all the way to -90 in a hypokalemic environment. What if you start with a membrane potential that's normally about -70? You have the normal potassium leak out of the cell, and now instead of hypokalemia, we're in hyperkalemia. We have a high amount of potassium outside the cell. This could be for many different reasons. It could be because other cells in the body are pushing its potassium out of the cell, which sometimes happens during an acidosis. It could also be that you have dietarily intaked more potassium than you need. So if you're in a hyperkalemic environment, membrane potential rises. It becomes less negative. There's less of a driving force for potassium to want to leave the cell. It's inhibited because the driving force is not there to the same extent. So we call that movement from -70 to -50 a depolarization. If you haven't reached threshold yet, that's okay. That's an action potential. We'll get to that soon. But what you're doing is depolarizing. If you go from -70 to a lower number, we are hyperpolarizing. It's easy to think of these two values if you look at them on a graph that uses membrane potential. Going up is depolarization, going down is hyperpolarization. Having a different concentration isn't the only thing that affects membrane potential. Currents can also change membrane potential. For example, once you open up channels that were initially closed. So what would we have initially closed? We had sodium channels closed, calcium channels were closed, chloride channels were closed. What happens if you open them up? Membrane potential changes. So here, this is showing you an example of opening up a sodium channel, and you can see a large change in membrane potential as there's an inward flux of sodium. So sodium influx allows for a depolarization. Why? Because its Nernst equation value was around 61 millivolts. So as it travels in, membrane potential rises. How about potassium? If you opened up even more potassium channels than what are open at rest, how would that change membrane potential? In this case, you would have a loss of potassium, so that would hyperpolarize the membrane. The conductance moves out, but the voltage goes down. So you can see how currents change this whole process.